Welcome to another NenTot Tuesday. I'm Mo with the Division of Agriculture. Today I've got Kevin Petrone to talk about some of the water resources and the test wells that were drilled in 2025. Good morning, Kevin. Could you let the audience know who you are?
Hey, good morning. I'm Kevin Petrone. I'm a hydrologist within the Alaska Department of Natural Resources, the Division of Mining, Land, and Water. And we're also within the water section in a small unit called the Alaska Hydrologic Survey. So I'm giving the main presentation here today, and Adam Daniels is also on the line. Adam did a lot of the field work for this, and he's a hydrologist who works with me based in Fairbanks.
Yeah, I recall
Thanks for having
there
me.
in the project area with Adam looking at the 1981 well for an afternoon last year. So,
oh, excellent.
Welcome. Go ahead and start your presentation, Kevin.
All right, great. Yeah. Well, thanks for having us, and I will share my screen. So, as I mentioned, we're generally discussing the Nenana-Totchaket groundwater resources and the results of the summer 2025 well drilling efforts. And this is just a few examples here of a drilling process on the left. I'm sure most folks know what groundwater wells look like at the surface. You may have one at your home, but this is just a few feet of casing sticking up. And this is what we'll discuss this one a little bit. This is the 1981 ag well. Okay, so overall there are 5 wells in the Nenana-Totchaket study area west of Nenana. You can see on this map we have wells 1, 2, and 3, and these were drilled in 2025. And then we also have what we call the 1981 ag well and the Nunivak #2 well. Okay, so before we get into drilling efforts, I just want to give a little bit of background on efforts in this area, which were started. Agricultural development was first thought about and started in the 1980s. So again, before I get to that, I just wanted to quickly discuss the geology of the area. Okay, these are all the well locations overlaying on the geologic map of Alaska, and you can see this map at the link below, the interactive geology map. And overall in the area, we have unconsolidated superficial deposits. And this is just a catch-all term for many of the areas where we find groundwater in Alaska. It's a mixture of alluvial material, glacial outwash material from end, lateral, and ground moraines, glacial deposits, material that was scoured and deposited since the last glacial maximum. However, some of the alluvial material that's in here could be much older than just the last 10,000 years. Perhaps it could be we could go back through several glacial advances and retreats in this area. So glaciers were covering the area in the Nenana Valley, whereas from my recollection in Fairbanks, in the Tanana Valley, there was not glaciers were not present because it was too dry, but they were present here, closer to the Alaska range. So we do have glacial deposits in the area. Okay, so from the surface we can see what the geology is, but it's often harder to know what's happening at depth. And so what we see at the surface isn't always what we find at depth. Let's take a look at this 1981 ag well. So as I mentioned, this was drilled in March of 1981 as part of the first efforts to develop agriculture in the area. And it's in the northern part of the study area. Okay, and this well was really abandoned for a few decades, and we with a bunch of tromping around, Adam and Mo and other folks were able to find this well last summer, and we redeveloped it, and now we have it instrumented for groundwater levels, which I'll show a little bit later. But on the left here, we have the well log for this well. The well is 190 something feet deep. And you can see the geology here is these dune sand deposits, and that goes to around 100 feet, and then alluvial aquifer system below that. And the well is screened from about 170 to 190. And so this is the area, this is the aquifer that's being encountered, that's being accessed by this well, okay? It's this zone from 170 to 190 feet below the ground surface. And what's worth noting is the groundwater level, although the well is screened at this level, the groundwater is 100 feet higher than the well screen, which indicates this is in a confined aquifer. And the water, the pore spaces in this zone from 170 to 190 are under pressure. And so the piezometric surface is just below 100 feet. So we have quite a bit of groundwater storage in this well.
It does not appear that it was frozen when they drilled it. Would they record those kind of facts back in the 80s?
That's a good point. There was a thermistor installed, 30-foot. You can see this note here. There was a 30-foot thermistor installed 10 feet from the well itself. I don't have those results in front of us. I believe it was frozen. Adam, do you remember? We can take a closer look at those data.
I sprung that on you unannounced. Sorry about that.
No, that's okay. We've looked at some of the borehole data that goes down to 30 feet. I don't recall if we have the actual data for this thermistor string or temperature string that was installed at this location, but we could find that with some more digging. Okay. So that's the first well. These are the two pre-existing wells. So then let's move on to the second one, which we call the Nunivak well. And this well was drilled during an oil and gas exploration study done by Doyon. And the well was drilled in 2013. And this well is deeper than the last one we just looked at. I believe it's over 300 feet. Unfortunately, we don't have a detailed well log of this well with the lithology, but we do have a description of the drilling process written by the driller, and we do have a pump test. So a pump test was performed after the well was drilled. A pump was installed down in the well, I believe at 250 feet, and they pumped at quite a high volume, 750 gallons per minute. Okay, and there was drawdown at this period, but the objective of the driller in doing this pump test is to stress the aquifer and see what the maximum capacity of the well is. And so if we were only pumping at a couple hundred gallons per minute, I expect you would see much less drawdown than we observed in 2013. Okay, so that's and again, you can see this is the location of the Nunivak well. Okay, so those are the pre-existing wells that we had in the study area, and based on those two wells, we expected to see continuous or consistent aquifers over the study area. And this shows one of the drilling pads. So there were drilling pads. So first of all, the well locations were decided by the Division of Mining, Land, and Water, the land sales group, in collaboration with Division of Ag, and the well locations were based on the parcels that are going to be developed. So it was really directed by the land sales and the parcel development of the area. But anyway, we chose 3 locations for these wells, and we developed drilling pads, and the drilling contract went out for bid through a competitive bidding process, and that was awarded to MW Drilling. And MW is one of the oldest and most experienced drillers in the state, so we're really happy that they did this work with us. Okay, so let's first look at well number 1. Well number 1 is in the eastern part of the study area. And we can see this is the well log. Just a snip of a clip of the well log. That, and by the way, these are all these well logs are in WELTS, which is the well log tracking system that our group, the Alaska Hydrologic Survey, manages. We take all well drillers' logs. They're by statute and regulation, well drillers are required to send well logs to us, and we enter them into our database, and we enter the borehole lithology and any information about the water yield, the static water level, and that information is captured. And we have over 40,000 well logs in our database.
Kevin?
So, yeah, go ahead.
So if, this is NenTot Tuesday, so we're talking about the Nenana-Totchaket Ag Project, but if someone wanted to know about the wells that are in Delta Junction or in Point McKenzie, other ag areas of Alaska, they could still use the WELTS log to look at those areas, correct?
Yes, correct. We cover the entire state. So we have over 40,000 well logs throughout the state, and you can follow these links and search by map. You can search by parcel. You can search by owner, driller. So a lot of our work, a good part of our work, is kind of servicing that database and answering questions by the public if they have questions or they're trying to find their well log.
It sounds like an amazing resource. Excellent.
Yeah, and also the drillers use it to, if they're going to drill in an area and there are well logs in the area, they're going to, they can just sit there on their phone or a tablet in the field and look at the surrounding wells in the area, and that will give them an idea of what kind of material, what kind of casing they need to drill a well, where they might encounter water. So it's a great resource for that. Okay, so this is well number one. So overall, well number one, we did find a gravel aquifer from roughly 220 to 230 feet below ground surface. And this gravel zone produced between 20 and 30 gallons per minute. And this is a reasonable water yield, quite good for a domestic well. And it could be used, on a parcel scale still for water supply. But we did find frozen soils above and below the water zone. Okay, so that's well number one. Well number two, this well is closest to the Nunivak well, which I just showed, which was several hundred gallons per minute in the pump test. So we expected, based on the data, the limited data we had, we expected that we might see water in this location, since it was only a few thousand feet from the Nunivak well. But unfortunately, this well was frozen down to about 270 feet. And although there was gravel below that and possibly thawed, the drillers did not find any water in this location. Okay, so let's move on. Go ahead.
That's mysterious that within 3,000 feet, you go from 350 gallons a minute to not finding anything. So that's.
Yeah, I agree. Well, I learned something. We learned something here.
Yep.
Yeah, but well, number three, as they say, third time lucky. We were very relieved that we found a thick, 40-foot thick aquifer zone, water-bearing gravel zone in well number three, and this is in the western part of the study area. So you can see the profile is similar to what the other two wells showed us. We have a lot of silty sand and gravel, but we did find this water-bearing gravel zone from about 250 to 270. And below that is also is clay. So there's a confining zone above and below this water-bearing gravel zone. And because we found significant water in this well, we decided to conduct a pump test. So after the well was developed, the drillers put a pump down the well and pumped at 350 gallons per minute. Okay, and this is the result of the pump test analysis that Adam performed. This is called the Cooper-Jacob method for confined aquifer, and it takes um, a fit of the drawdown. So this is drawdown on the y-axis and time, logarithmic time on the x-axis. And the Cooper-Jacob method relies on a curve fit of this drawdown over time, and this did fall into a kind of a linear relationship which was a good match for the Cooper-Jacob method. I won't get too much into the results of this, but except to show you that the K value, and the K value is what hydrogeologists call hydraulic conductivity, the Darcy hydraulic conductivity, okay? And this really describes the velocity of water moving through the aquifer medium, through that gravel. And the estimate that we got from the Cooper-Jacob method is 800 feet per day. And we can see, we can compare this to different aquifer materials, and 800 feet is right within the range of a gravel aquifer, okay? So you might expect gravel aquifers to be like from 90 to 3,000 feet per day. And we're right within that range at 800 feet per day. And again, this is a highly productive well that could be used for commercial purposes. It could be used as a high capacity well for potable water, for instance, and also obviously agriculture and irrigation. So we're very pleased that our third well was a high producer.
And none of the soil was frozen. That's another interesting thing, is that the other wells all had frozen soils, and this one did not encounter frozen soils. So that sort of indicates the permafrost is non-continuous or contiguous, and
yeah, exactly,
or mysterious.
Yeah, and it's not uncommon to the area west of Nenana is in the discontinuous permafrost area. So it's not uncommon to find permafrost when you drill wells, but still within that discontinuous permafrost area, we do see, in at least 4 out of the 5 wells that are in the area, that they do have gravel producing. They do have gravel aquifers that produce adequate water, even though there's some permafrost around. So. Yeah, okay, so the last thing I'll mention on this well, on well number 3, are the water quality results. So after the pump test was performed, the well was developed. We had, many thousands of gallons moving, hundreds of thousands of gallons over a 24-hour pump test that gave us a good connection with the aquifer, and after that, we were able to take a sample for water quality. And these are the results of the water quality. And what's worth noting here is we also have in the report that followed the 1981 drilling efforts, there was water quality analyzed from that well. So that's what's shown here on the right column, and on the left are the results of well number 3 that was done last summer. And it was quite surprising that the chemistry is very similar between the 2 wells. So it does indicate that it suggests that if we find more aquifers in the area, the water quality results might be consistent with what we found in the 2 wells so far. So let's run through this. Alkalinity. These are multiple measurements here, so just separated by a semicolon. The replicates, I guess. So we have alkalinity, hardness, total dissolved solids. Specific conductance is quite low. I remember from a grad student measuring specific conductance of the water at the university, and it was higher than this amount, which is, we're in the hundreds, a couple hundred microohms per centimeter, or it's also equivalent to microsiemens per centimeter. So that's a measure of the ion content, dissolved ion content, the conductance of the water. Let's move down here. We can see major ions seem to be, we're seeing calcium and sodium, but low in chloride, fluoride, nitrate, phosphate, sulfate is low. Yeah, so it does appear to be reasonable water quality for drinking water or for irrigation from this first slide. If we go to our next slide, the metals are, yeah, still very suitable for irrigation. You can note here that arsenic is above the drinking water standard, but it's still within the range of many wells that you might see in the Fairbanks area. Also worth noting, we had some iron and magnesium, but these water quality results are very typical of what you might find in interior Alaska. Last thing I'll mention about arsenic is this was just a data provided by the Division of Geologic and Geophysical Surveys. Just a little pamphlet here on arsenic, naturally occurring arsenic in Alaska. And they indicate here that, yes, the drinking water standard for arsenic is 10 micrograms per liter, or ppbs, parts per billion. But for irrigation, 100 ppbs is typically kind of a guideline for irrigation or for livestock. And you can see some of the ranges that you might find for arsenic in interior Alaska. So we're definitely at the low end of what we might see for arsenic in interior Alaska. Yeah. Oh, the last thing I'll mention is that we have instrumented the 1981 ag well. Since this well isn't going to be used for water supply, it was originally set up as a monitoring well. We decided to reestablish that. And you can see this is a photo of Adam putting a conductance tape down the well. And he uses this to manually check the pressure transducer. So now we have a pressure transducer in this well, which measures the water height above it. And he takes manual measurements a few times a year to calibrate or check this water level against the manual measurements. And these groundwater levels are pretty typical for what we see. We have a number of monitoring wells in south central Alaska. This is our first in the northern region. But this is a typical pattern that we might see for groundwater levels, in that the groundwater slowly drops throughout the winter when infiltration is low, infiltration from snow or above ground precip. That's what recharges the groundwater system. So when things are frozen, we see this groundwater level dropping, and it reaches a low point kind of in April. But then at the onset of breakup, we see a rise in the groundwater level, and reaching a maximum kind of in late summer. So yes, this was a nice result, that the groundwater levels do seem to be connected to the surface hydrologic cycle, and are connected to that snow and rain that's infiltrating and recharging the groundwater system. So that tells me that the groundwater system is not necessarily very old, but and we likely have groundwater moving through the study area, likely to from the south to the north.
And the project area has the Kantishna River on the west and the Nenana River on the east, so it kind of makes sense that it's all flowing through there, because we're a mound of sand between the two rivers.
Yeah, and generally groundwater will follow the surface gradient. So we expect to see a flow from the south to the north, and capturing this alluvial area, as you mentioned, between the Kantishna and the Nenana rivers, generally moving north towards the Tanana. Does that make sense?
Yep.
Yeah, great. Yeah, so overall, this is these are all the wells in the study area. This was a slide that Mo had put together here with, and this red outline is the agricultural area. And we can see the well depths, casing diameters, and these are the Welts numbers again. If you want to dig more into these wells, you can search by the Welts ID, which is shown here. These are the development test or pump test volumes. And one other thing worth noting that I hadn't mentioned earlier is that when these pump tests were stopped, okay, the drillers stopped pumping, the recovery to the static water level, the water level that we observed prior to pumping, was quite rapid. So in well number 3, that new well that we drilled, the recovery to static water level was 2 minutes. And in that Nunavak well, that had a much higher pumping rate, it only took 30 minutes to recover. So it does indicate that the aquifer is receiving water, from the surroundings. And when we stop pumping, when we stop stressing that aquifer, it quickly recovers to the static water level. So it does appear there's an abundance of water, at least in those aquifers where we found them. All right, that's really it. Last slide. I know I've reiterated this a few times, but well number 1 had a water-bearing layer from at depth over 200 feet. Well number 2 was frozen down to 270 feet, no water below that zone. The Nunavak number 2 and well number 2. Yeah, it's worth noting that, as we mentioned earlier, although these wells were only 3,000 feet apart, well number 2 did not produce water, but the Nunavak produced 700 plus gallons per minute. So overall, where present, the water-bearing gravel aquifers are highly productive. But as we've seen, aquifers are not continuous over the entire project area. And that might be partly dependent on the individual kind of gravel zones that we find, and where it's more silty, where the hydraulic conductivity is lower, those areas might, it's hard to say exactly where the permafrost is present, but it might be related to the permeability of the silt sand, the mixture of silt sand and gravel that we see at depth. And lastly, I just wanted to mention that the water quality from the 2 wells that we've sampled so far are quite consistent between the wells and appears to be an acceptable range for irrigation water. Well, thanks. That's all I
have. Thank you. Did you have contact information in case
somebody
had some specific questions? Excellent.
Yeah, here we go. Here's our contact information on the last slide. So you can reach myself or Adam. These email addresses. Adam, as I mentioned, is based in Fairbanks, and I'm in Anchorage.
Thank you for the presentation today. I will let the audience know that we have some very draft plans to do some additional research regarding, possibly determining where those permafrost layers are and how they are across the project. But, nothing is firm yet, but we acknowledge that is still a question that we need to try to answer. So keep tuning in to NenTot Tuesdays. Thank you, Kevin and Adam, for joining us today. And this summer, there's going to be a Nenana Ag Expo on Saturday, June 6th at the Nenana Community Center. We're going to have some soil pits out there. You could come look at the wells of those locations if you wanted to, but it's going to be an opportunity to ask questions and meet with experts. So thank you for joining us today.
Thanks, Mo. Appreciate it. Thanks for having us.
Yep.
Bye.